So each of these sessions is only meant to take up to 40 minutes max, and that's a self-imposed limit because the Zoom room's actually going to close by 40 minutes, so it better be done. Um, I've done my best to break things up so that it's easy. My philosophy with math is I'm okay with skipping stuff that we don't need. What I'm not okay with is leaving gaps and not telling you that I'm leaving gaps. So what I'm going to be doing is all throughout, I'll always say what we're learning is this. The reason we're learning it because we're going to apply it in this way with AI. And I will tell you, hey, don't count on me for, getting you through math class because there's all of this stuff that I'm not teaching you. But with that being said, I'm going to dive straight into the first topic, which is really, really easy. And it's just basic graphing. And, you know, lots of you have been sending me videos about calculus and derivatives and matrices, so I'm sure this will be easy to you. And it should only take maybe 20-ish minutes. So I'm just going to get started. Um, as always, why are we learning what we're learning? Graphing is one of the simplest applications of AI. It's going to be a problem called regression that we're going to learn about, which is basically how do you take data and figure out what is the line of best fit that goes through it. So whether it's, hey, we have a bunch of data from this product we're manufacturing. We need to figure out if our computer chips, whether they're resistant enough to current surges. That's an example of when you might want to draw a line through data. And I say line, but the functions that we draw through the data, they don't have to be lines. They can be lots of very fancy, very many fancy shapes. So when it comes to computing, the basic thing we need to know is just how do we take equations and then put them on a graph. There's a lot more theory out there, how do you modify equations, how do you change up graphs, but for computation, that's all we need to know. So today I'm just going to quickly cover linear lines. Um, that's the most simple regression problem. I'm going to cover quadratic functions and how to graph them, and then finally polynomial functions. And those will pretty much get you through all the regression problems you'll ever need to do in machine learning. I'll tell you what some of the other functions are if you want to learn about them yourself. So I'm just going to start sharing my screen here. Any questions before I start? All right. So today, pretty simple. You do need, if you're watching this, you do need to have grade 8 knowledge, which is you need to understand what is written here, variables, equations, algebra, the basics of that. And the first thing I just want to point out is how do we interpret linear equations? So let's say you have an equation like this, y equals 2x plus 4, where you can take these variables, x and y, and assign different values to them. So let's say we put -1 as the value of x. 2 times -1, that's -2, plus 4, and that's +2. So y ends up being equal to +2. That's basic grade 8 math, so you got to understand that. Um, we can keep doing this for all of these different numbers. So we can put in a bunch of numbers for x and get corresponding outputs for y. Often in computing, we don't write equations like this, y equals 2x plus 4. What we often write these as is actually, we say f of x. And that's just like notation for a function where you have some input value, x, that's the variable, 2x plus 4, and that returns to the output of the function. So it's like you go from x to either y, you can call it that, or f of x. So these are just some notations to be familiar with, especially this one, because all the time when we're studying AI theory, all of the equations look like this. So that's basically the theory part you need to know. Now, Here's the fun part. I know all of you on this call have seen a Cartesian plane before. Okay, you take the values in the table, you graph it on a coordinate system where you have x on one axis, y on the other, and I can show you that right here, where I have x on one axis, y on the other. And literally what I did was, if I take -1, put it on x, here's -1, and then the y is 2. And I did that for all the points. Now, one thing that I want to point out here that most people don't point out, they're just like, okay, yeah, like it's math class, here's what we're doing. We're going to take the equations, turn them onto graphs. What they don't explain is this is just one way of visualizing the information we have. So this over here, this equation, that's like the abstract math representation of the information. Another representation is just this table, and that's more limited because you only have the information that you're given, whereas it has variables, it can represent many possibilities. And this visual representation, it still is just like another representation, but one of many. And that part is key because later on, we're going to start looking at what happens when we don't just have, say, an x and a y. What if we have another variable z? What if we have 1,000 other variables? And that starts to get very messy. It starts to mess with your head a lot. So that's why I just want to point this out here. This is just one representation, one visual representation out of many. And we're going to be learning about some cool other representations that I personally find fascinating later on. So right now, let's just focus on this. So y is equal to 2x plus 4. What we did was we took some x points, we put them into the equation, got some y values, and we plotted them on a graph. And what we can now do is we can actually plot the line of what we get when we connect all these points. So let's say I plot the line going from here to here. I can make it red just to match. That is basically our line. We can extend that if we want. So we can extrapolate, it's called. We can say, hey, if it's always just going straight, a line, then it'll continue to go straight. So we can just try and make this as straight as possible, going downwards and outwards. Yeah. You could probably do a better job, but it just extends in both directions. So we draw an arrow. And that is basically what the regression problem is. You take a bunch of data, so data points, those red dots, and you draw a line through it. Now, I want to quickly highlight one thing about this line. So as you notice, there's a special point here. Not too much theory, but there is one special point here. It's called the y-intercept. The reason is it goes through the y-axis. It's kind of like it just intercepted the y-axis. It hits the y-axis. And as you can see, that always happens when we set x equals to 0, as you can imagine, well, if we set x equal to 0 here, all of this just disappears and we're just left with the 4. So that's why we can say that the y-intercept is 4. And then the other concept to know here is the slope. So if I wanted to show off what the slope is, it's just like the slope of a ramp. It's basically if I go, say, one step in this direction, the x direction, how much do I go up in the y direction? So here we went from -1 to 0, that's +1. And here we went from 2 to 4, so that's +2. And the slope is represented by a special symbol, m. There's actually a French connection here. The reason why it's called m, as my grade 10 teacher explained to me, m is for monter in French, which means to climb. So slope, to climb, m. That's how we define it. How much do you go up versus how much do you go forward? Or rise over run, 2 over 1. So m in this case is 2. And you can see that corresponds with the 2 that I wonderfully crossed out here. So that's actually the general equation for any linear line. We just need two pieces of information, this y-intercept which was 4, and then the slope, m, which is 2. And that's how we write out any equation. This is the y-intercept. It's represented by a letter b. No cool French analogy here, unfortunately, just a random variable. But just to highlight something, later on, the way we're going to see this written in computer science is, again, we're going to say f of something, but we're going to use like random symbols. Like we could just put in this weird letter theta. We're going to say f of theta is equal to theta 1, where we say, you know, m is equal to theta 1x plus theta 2. Again, keep in mind, it doesn't matter what we name our variables. I just want to show you why we're learning this. So these are all the same things. It's just you can choose whatever variables you want. So that is linear lines. 2 pieces of information, y-intercept plus the slope. And all you need to know is how to graph it for computer science. Is that cool? Any questions? All right, well, let's do the same thing with quadratics. So quadratics are just another equation. So in this case, you know, the difference between this equation and the last one up here is that in this equation, there is a square term right here. Yay. And that square term changes what we call the equation, because why not? But it's just the same thing, just made more fancy. All you got to do is just take in some x values, like say -2, -1, 0, and you just plug it in. So -2 squared, that's 4. 2 times -2, that's -4, but you know, minus -4 is still +4. It's still the same thing. Take some x values, calculate this expression, see what y value gets out. And in the end, we have to do the same exact thing again. We just have to plot these things on a graph. So I can I have a wonderful fancy shape here. I like it. It's fun to play with. Get to adjust all these points. In real life, you just like draw a line of best fits. That's what they're called. In computer science too, we call them drawing a line of best fit, where you just take the data points you have and you just get a line that goes through all of them. That's that. And I'll just like do my own version connecting here. Yeah, close enough. And again, we would just draw these little arrows at the end. So 2 things I want to point out here. Very important, actually. One thing is this point over here is special. This point over here is the lowest point in this parabola. It has the smallest y value. You can see over here, the y value is 0. That's the smallest it gets. This is a very special point, okay? This is the vertex of the parabola. Now, not all parabolas have vertices that, you know, are the smallest, but the vertices are really important for us because in computer science, we focus a lot on being able to find these vertices. Imagine this vertex, this function isn't just like x's and y randomly. Imagine the x instead represented. I spend this amount of money repairing my equipment in a factory, and y is like the amount of profitability I have because my machines work that much efficiently. In computer science, these types of problems are called optimization problems, where you want to figure out like what is the most extreme version of something. So let's say you spend the least amount of money, you get the least productivity here. And oftentimes in AI, we have a bunch of problems that are entirely designed about this principle. How do we find the lowest vertex of different functions? Again, keep in mind, I can just call these things functions. At the end of the day, it's the same thing. Whether you say y equals x squared minus 2x plus 1, or f of x, I could write that. It just means the same thing. And in computer science, we're going to see this notation often. Aside from that, nothing too complicated. There are a lot of things that you can explore with parabolas that I'm not getting into. Just so you're aware, in grade 10, you'll spend all day just going over those things for no reason. I'm sure there's a reason, but I don't think there is. whatever. Your math teacher can argue about that. But again, here's the general equation. We're just taking a bunch of random variables, A, B, C. I'll show you what we would write in computer science again, which is f of some random variable. This is called theta. It doesn't have to be theta. It can be A, B, C. All of that is fine. We can say theta 1 x squared plus theta 2 x plus theta 3. You get the idea. It doesn't matter what we call the variables. Just be aware of that, because later on, like in computer science textbooks, they always look so weird and bizarre. Really, it's just the same thing. They just change the variables. So anyways, that's that. Here's a bonus. If you want to get a preview of grade 10 and what you spend all day doing for some reason or the other, what you do is you take that first equation we had, which is this one, y equals x squared minus 2x plus 1, and then you just randomly mess with it. Like, what if I added a negative here? What would happen? What if I added a 3 here? What would happen? What if I added a 2 here? What would happen? And you can actually go to this website, desmos.com, and you can just type in these equations, see what happens, and see if you can notice any patterns. That is all of grade 10, basically. So the last thing we're going to talk about is finally graphing polynomials. And it's the same general idea as ever. What's changed now, again, notice, now we have an exponent of 3 here. Before, we only had an exponent of 2. So that's why we call these functions different names. And keep in mind, functions just means, y equals this thing, but you just call it a different name, because why not? Here we have a exponent to the 4, so that's again different from the exponent to the 3. Again, they're different functions. What we call these exponents are actually what's called the degree of the function. So here, we just say that the largest degree is 3. The largest exponent that we see is 3. So it's just a degree 3 function. Over here, this is a degree 4 function because the largest exponent is 4. Just a random piece of trivia that you never need to know, except in math, you need to know it then. But again, we're just always doing the same thing. Take a bunch of x values, put them in, and calculate what the output is. You could literally pause right now if you don't trust me or like, oh, he's messing with me. You could put it in, you could calculate, okay, -2, put it in here, calculate the value, eventually you get 16. Or over here, I did them for the blue function. Here, these are weird, bizarre values, I know, whatever. You can just put in any value you want, x, and you'll get out an output y. I've graphed these over here. These are actually from Desmos. This is what a Desmos graph looks like. They're fun to play with. Here's a random bit of trivia. If you're interested, search up Desmos Arts. You'll see all the cool things you can do with math functions, just making art out of them. But over here, we have this x cubed plus 2x squared minus 4x plus 8, that function. It's just graphed over here. Bunch of points. You put a line through them. Pretty simple, as always. That's all we need to know in computer science. I will point out a bit of trivia, which is that over here, you see that the degree of this function is 3, because the highest exponent is 3. And you'll notice we have 1, 2 curves. Over here, the degree of this function is 4. You see, 1, 2, 3, 4. That's the highest exponent. Here we have 1, 2, 3 curves. And if you noted, back with degree 2, what I called a quadratic function, this was degree 2, you only have 1 curve. Yay, lots of math trivia. Except when you're actually in math, then they'll make you memorize this. So yeah, sorry for you, but you'll have to learn that. But that is it. That's simple. You just got to figure out what the numbers are that go in, and you put it out on a graph. Any questions? Cool. So as I said, the most important things to keep in mind, at the end of the day, we don't need to do a lot of complicated math things. They have weird words like factoring. I don't like that word, factoring. It's such a weird word. Sounds odd. We don't need to worry about that. All we need to know is take a bunch of numbers, plug them into the equation, get out a value. That's all we need to know. And then we can put them on different visualizations. This is one of many. I'll show you some different ones later, and I think they're cooler. So that's how you need to know. And the last thing you need to know is we don't always like use these random variables. We can put in whatever variables we assign. I like to joke that, you know, if math teachers were nice, they would be like y equals smiley face times x squared plus like frowny face. That's fine too. You can do that. You can just put in emojis. That's fine. It doesn't matter which variables you put. So just be ready when you have like these weird messy equations. It's all fine. And that is basically the intro that we need to graphing. Again, that is what we need to know for regression. And next week we're gonna cover something new. We're gonna go over calculus. And calculus is gonna come back to this thing, this lovely graph. So I look forward to seeing you guys in that week's video. Does that sound good? Any last words? Ominously, he leans closer, waiting for the last words. No? Alright, so I'll just stop screen sharing then. And we are done.